Okay. Okay, I got it, and then view and full screen mode. Okay, now you see my screen only with the presentation, right?
Yes.
Awesome.
Yeah.
Okay, so today I will talk about strict units in the sphere spectrum. So this is a quite recent project, so it's really in progress. And of course, I will explain what are units, what are strict units, and what is the sphere spectrum, although this I believe some of you already know. And the goal of the project is to compute the combination of all these words. And what I will present is a work in progress again, dedicated to computing those invariants for the sphere. So let me start with discussing a very classical notion as a motivation. It always also will play a role in the result in the end. So if we have an ordinary commutative ring in the usual sense, abelian group with multiplication, then you can attach to it three natural important abelian groups. So the first is the additive group, which just forgets the multiplication and remembers only the abelian group. So I denote it by GA, and it's like the underlying set of R with plus, which is the multiplication. The other is the multiplicative group, GM of R, which is the underlying, the subset of invertible elements, and the multiplication is given by the product in the ring. And then there is also what I denote by class group of R, but it's actually usually called the Picard group, but I will denote it here by CL for classes, which is the group of isomorphism classes of invertible R modules. So if we want to think about it in a slightly sophisticated way, it's the invertible elements with respect to the tensor product in the category of R modules, which I want to think as some kind of a categorification of R, or a one categorical level up manifestation of the ring R. And those are three very important invariants we can assign to a ring. They all play a role in like geometry, number theory, and all sort of things. And the point is that all those groups have analogs in higher algebra. And before I say what are the analogs, let me first say what I mean by higher algebra. So this higher algebra is algebra done in the infinity category of spectra, for me at least. And let me recall quickly what that is. So we have the infinity category of spaces that I denote by S here. And there is the infinity category of commutative monoids in this infinity category of spaces. This is like the higher categorical analog of commutative monoids, usual commutative monoids. And those commutative monoids are, of course, in the higher categorical sense. So if you like, infinity monoids in spaces, so including a lot of higher coherence, encoding, commutativity, and associativity of the multiplication. Inside it, there is a full subcategory, which I denote by Simon group of spaces, or group-like commutative monoids. And those are the ones that are supposed to resemble groups. And one way to say it quickly is that this upper unipotent matrix, when acting on two copies of X, is an isomorphism. So that's the inverse of this matrix involves the minus sign. So this is how we know that there is a minus. Now there is the classical definition of the infinity category of spectra, which is just the inverse limit over the loop functor on the infinity category of pointed spaces, or if you like, this is an infinite loop spaces definition of spectra. And inside it, there is a full subcategory of connective spectra, which are on just those spectra for which the homotopy groups, which make sense because loop have a well-defined behavior with respect to homotopy groups, only concentrated in non-negative degrees. As you see, this is the same as, well, the negative homotopy groups, which now make sense because we have infinite loopings, are zero. And then there is the May recognition principle, which tells us that those two things are the same. So this classical homotopy theoretic definition of spectra have a full subcategory of connective spectra, which can algebraically define as some kind of commutative monoids with a property that they want to be like groups. So we can think of connective spectra, or maybe more generally spectra, as a higher categorical or homotopy theoretic analog of abelian groups, where we want to do higher algebra. So the slogan for this theorem is that secretly, whenever we have a group-like multiplication, which is coherently commutative and associative, secretly it is given by loop concatenation. But the point is that in this talk, I would like to talk about multiplications which are given a priori and not think of them as loop concatenation, but think of them on their own right. So I would always prefer the right-hand manifestation and think of connective spectra in this form. So I want to think of connective spectra as group like commutative monoids and spectra as some kind of a version where I have negative homotopy groups. Okay, so the concept of higher algebra is replacing abelian groups, their tensor product, and correspondingly the unit, which is the integers, by spectra, their smash product, which I denote again by tensor, and their unit, which is known as the sphere spectrum, whose homotopy groups are the stable homotopy groups of spheres. So a very interesting object. Closely related is homological algebra, which for me just means that instead of abelian groups, we look at the derived category of Z modules or the derived category of abelian groups, so derived tensor product, and the integers as a unit, but it turns out to be something we can read from the spectral version, because the derived category of abelian groups, it's just modules over the ring Z, which now I think as a commutative ring in spectra. So modules over it in spectra is just the same as the derived category, or rather infinity categorical enhancements of that. And the derived tensor product become now just the tensor product or the smash product over Z. So it's nice, we get some theory which is somehow more fundamental than homological algebra in some sense. And now we can do higher commutative algebra, namely we can replace commutative rings or commutative algebras in abelian groups by commutative algebras in spectra, which are classically known as E-infinity rings. And everything I said about commutative rings before, we now want to generalize to infinity rings. So we want to talk about units in such infinity rings. So what's an infinity ring? It's some kind of a spectrum which is coming together with a multiplication which is coherently commutative and associative. And we can assign to it 3 natural connective spectra. Remember, for me, connective spectra are grouped like commutative monoids, so I need to give a space together with a multiplication. So one of them is just the additive group, which in this case, it's just the spectrum, which is the connective cover of R, so we ignore negative homotopy groups. But if I want to think of it not as a connective spectrum, but as a group like commutative monoid, it's the underlying space of R endowed with the addition of R. Another one is GL1 of R, or the multiplicative group of R, or the group of units of R, which is a subspace of the underlying space consisting of those elements which are invertible up to homotopy with respect to the multiplication. And the spectrum structure or the multiplication is given by just the multiplication provided by R. So that's GL1 of R. It's a subspace of the connective cover when we forget the spectrum structure. But of course, the spectrum structure makes it much richer. And then there is the Picard spectrum of R, which is what happens when we replace R by its category of modules, take the multiplicative group of that with respect to the tensor product. So in other words, it's the space of tensor invertible R modules, where we ignore non-invertible maps and non-invertible elements, and the multiplication comes from the tensor product. Okay, and now those 2 things in higher algebra already are related in a very nice way, which is a little bit harder to see in classical algebra. So first thing is that the Picard spectrum of R, which is a connective spectrum, its loop spectrum, or rather the loop space together with the pointwise multiplication of loops, is just GL1 of R. And the reason is that the base point, the 0 element of pic R, or the unit element, is just R itself, and its automorphisms are, well, R. So the units, the invertible automorphisms are R cross. And the relation between GL1 and the additive group is a little bit more complicated, but one thing we can say about it is that after we kill the zeros homotopy group, so from pi1 and above, or rather the connected cover of both, are the same spaces. So the connected component of the identity in those 2 spectra are the same space. And the reason is that loops that start at the identity have to go only through invertible endomorphisms. But note, however, that this equivalence is slightly misleading. It's only of spaces. It's as spectra, they are very different. The multiplication on the right-hand side is given by the addition on R, and on the left-hand side by the multiplication of R, which are different operations in general. So a natural question is how to study GL1 of R, and more generally pic R, which is more complicated by what's happening on the first part of the slide. as spectra, so remembering the operation, not only the underlying space. So before we go into that, let me just return to the example of ordinary rings, which is already slightly interesting when we think about them as infinity rings. So if we have an ordinary connected ring, ignore the connected for now, there is a generalization to non-connected rings. We can think of it as an infinity ring because abelian groups is a full subcategory of spectra, of connective spectra, actually of spectra, yes, of those spectra which have discrete underlying space. So we can now study the homotopy groups of the various spectra we defined. So pi0 of the Picard spectrum of R, remember now R modules is actually the derived category of R modules. So it have a component corresponding to invertible R modules and another one corresponding to the option to make shifts of complexes of R modules or R module spectra. You can suspend or desuspend them. So there is a Z component for the suspensions and another component for the classical Picard group. And here we use the connected, otherwise this Z have to be replaced by something else. And the pi1 of the Picard is again just pi0 of GL1, which is just R cross, the discrete spectrum, which is the abelian group R cross. So we know the homotopy groups, and we can ask, okay, maybe this is just a product of Heisenberg-MacLane spectra. I mean, maybe the homotopy groups are not glued in any interesting way, but maybe not. But in general, that means that we have a Postnikov tower, which have like the class group of R times Z at the bottom, and then at the pi1 we have the suspension of R cross. But the extension is non-trivial, and one way to see it is that if we take the Hopf element, or in general non-trivial, if we take the Hopf element in pi1 of the sphere, so the homotopy groups of sphere act on the homotopy group of every spectrum. If we take the Picard spectrum of an ordinary ring and let this Hopf element act on the suspension of R, we get -1. So this means that the spectrum cannot decompose into Heisenberg-MacLane spaces because the pi0 and pi1 are connected by eta, non-trivial. So already if we start with an ordinary ring, its Picard spectrum is a non-trivial spectrum, which I find pretty fascinating. And we see that that means that if we take an infinity ring, we expect the Picard spectrum to be very interesting, because already for an ordinary ring, it was somewhat interesting. So how do we understand the extra structure a spectrum have on top of an underlying space? So one interesting invariant of a spectrum is the so-called total multiplication maps, or they have many other names. It's some kind of a name I know, but I think it is known by many other names as well. So what this map is, so if we have a spectrum and we have an integer m, well, it comes equipped with a multiplication by m map that goes from x to x, which adds m elements of x. But in fact, this map's refined to a map from x to the x-valued cohomology of the classifying space of the symmetry group on m letters. And the reason is that if we sum up m elements, then we have the freedom to permute them. This is part of the data of being a commutative monoid. And because they're all the same, this turns into self-symmetries of the sum. So we get a map that refines to a map on to this x to the power of b sigma m, in the sense that spectra are powered over spaces. Again, how to think about it is that the total multiplication by m map is given by summing a point of x m times, but now we remember the permutation action rather than observing that this point is preserved by it. Just for you to know, if you want to know how this is defined, one way to define is that this is just a transfer map along the inclusion of the base point inside the classifying space, which is a covering space. So it have a transfer map in spectrum. And here are various examples. So if x is GL1 of R, then this total multiplication by m map is given by restricting the total mth power operation of R to the multiplicative group, which is now a group homomorphism, or rather a connective spectrum homomorphism. If x is the Picard spectrum, well, I will just change the letters. It's still pretty formal, but what the idea is that we're tensoring an R module with itself m times, and remember the cyclic action on the tensor object. So in particular, this has to do with the symmetry of the symmetric monoidal structure on the category of R modules. And another example, which is somewhat trivial, but plays a very crucial role in what I'm going to say next. If we take X to be Z considered as a discrete connective spectrum, then theta M of A is just MA, and the sigma M action is trivial. Namely, because all the components of Z are contractible, every map from B sigma M to Z have to be to land on some connected component, and then there is no options because this connected component is contractible. So Z is some kind of a spectrum for which all M's total multiplication maps are trivialized. And this is a very crucial feature of this ring or object. And of course, this will be true for any other abelian group as well. In fact, something stronger is true. So what happened when we consider the total multiplication by M maps on a spectrum which have a Z module structure, namely in the context of homological algebra? So here is the claim. So if we let pi be the terminal map projecting B sigma M to a point, and we have any X in the derived category of Z, remember this is the same as a spectrum endowed with a Z module structure. Then we have the following commutative square. So we can look at the total multiplication by M map, and it decomposes as the naive multiplication by M map, and then the constant map, the map that produces constant maps from X to the B sigma M. So, or if you like, the pullback map on cohomology, on X valued cohomology from the point to B sigma M. So in other words, not only Z have the property, not only the integers have the properties that that all its total power maps are trivialized. This is true for any Z module. But the proof more or less reduces to the case of C. But anyway, I want you to think about this as a characteristic property of the derived category of the integers. So Z is some kind of an object, such that modules of this object have come together with an absolutely canonical trivialization of all the multiplication by M maps. And this is a major difference between homological algebra and higher algebra. In higher algebra, those maps are very rich and interesting. In homological algebra, they all canonically trivialized. Trivialized not in the sense that they are zero, but in the sense that they are constant. So this leads to the following idea. If we have a spectrum, we can produce a Z module in actually two different ways. One of them is the more usual one, is tensoring with Z, but today I want to focus on the option of mapping out of Z and get a Z module by letting Z act on the source of the mapping spectrum. And this is somehow a way to canonically strictify or constantify all the total multiplication by M maps. In particular, the unit map, I mean, this home from Z to X participates in, is the right adjoint of the forgetful functor from Z modules to spectra. And the co-unit map that goes from the maps from Z to X, namely the map that evaluates at 1, cuts out of X strict elements, namely elements which strictly commute with themselves, such that when we add them with themselves M times and we let the permutations act on the factors or on the summands, the action is trivial. Like all those things are canonically the same. All ways to organize the sum of M copies of X are canonically the same. And therefore, I mean, this is some kind of an interesting higher algebraic invariant of a spectrum, which asks how hard it is to trivialize the total multiplication by M maps. So as this map cuts a smaller piece of X, X is more complicated as a spectrum on top of its homotopy group, so to say. So just a side note, if you're a Z module, you're always a product of your homotopy groups suitably suspended. So this is like really something that measures the complexity of the glue of the spectrum somehow. So now we can define the following two objects. So one of them, so if we have an infinity ring R, we can consider the strict locus of GL1 of R, which are strictly invertible elements of R, and we denote it by GM of R, and this is just the mapping spectrum from Z to GL1 of R. And we can also deloop it once and consider the strict Picard spectrum of R, which is maps of connective spectra from Z to the Picard spectrum of R. And both are objects of D of Z. Again, this functor is the right adjoint to the forgetful from Z modules to spectra. And because this is a right adjoint, it preserves loops. So it's still true that loops of the strict Picard spectrum is GM. And those invariants are very interesting for us to study because they cut some very distinguished piece of the Picard and the Picard spectrum and GL1. In particular, if you remember GL1, the homotopy groups of GL1 of R are like pi0 is just R cross, and all higher homotopy groups are the same as of R. But GM of R is going to be very different from maps from Z to R itself. So it's a way to distinguish those spectra, although they have very close homotopy groups. So here is a first example of a computation of the strict of GM. So if En is a loop in Tate theory of a formal group of height n over an algebraically closed field kappa of characteristic B, so for every number n and every formal group of height n over such a field, there is a theory called Dn, the loop in Tate theory. And it is a very classical object. I will not discuss it too much. But the homotopy groups of GM of En are computed as follows. So for I equals 0, it is just K cross, namely the units of kappa itself. And at I equals n plus 1, so one above the height of the theory, we have a copy of ZP. And all the others are 0. And this is a theorem of Hawkins and Lurie. It is unpublished. It was discussed in the Thursday seminar of Harvard University for a while. But in any case, this is, as you see, very different from GL1, for example, because the pi star of En is the following. It is the width vectors of kappa, so something that is like W of kappa to kappa is like ZP to FP, so it's much larger. It have all sorts of powers of P inside. Then you also have to add several formal variables to it, and then to periodize it by an element, invertible element U of degree 2. So very large ring, and for example, GL1 of En have enormous homotopy groups compared to what's written here. So only a tiny bit of En consists of strict units. And in fact, the map from the strict units to the units capture only the Teichmüller lifts of the elements of kappa itself inside the width vectors. So it's really very hard to be a strict unit of En compared to how much hard it is to be an element of En. Yeah, so this is about Lubin-Tate theory. And now we would like to think about the initial example of the sphere spectrum. So we would like to know what is GM of the sphere. This will be, the sphere is the unit of spectra. So this is the first question to ask if we have something that we assign to infinity rings. So let me add an auxiliary player to the game. So if I will denote by SP the P completion of the sphere. So the sphere itself is somehow assembled from its various P completions and its rationalization. I will discuss it later. So it's interesting also to know what happened locally at a specific prime, namely for the P completion. And here is the theorem. So again, it's in progress. I'm still writing it. So of course, this is very recent. So the strict Picard spectrum of the P-complete sphere is just the suspension of FP cross. So it's an Eilenberg-MacLane spectrum with a single homotopy group, which is pi1. And this pi1 is FP cross. So a group of size P minus 1. And the strict Picard spectrum of the sphere is a discrete spectrum Z hat, where Z hat is the profinite completion of the integers. So it have no higher homotopy groups, and pi0 is the profinite completion of C. So this is what I want to explain today. So I will discuss these results in detail and why they're true. And maybe then also some generalization of A. Yeah, okay. So of course, one corollary of that is that we can now compute GM, because GM is just the loop space of the strict Picard. And GM of the P-complete sphere is now just FP cross. And this FP cross is again represented by the Teichmüller representatives of elements of FP cross in ZP cross inside GL1 of the P-complete sphere. So we also know which elements can be strictified. So the statement is that those elements can uniquely be strictified and no others. And Interestingly, the sphere itself have no strict units at all. So in the highly coherent sense that the space of strictly invertible sphere elements is contractible. So a little disappointing. I would be much happier to tell you about the cool strict units, but I can't. On the other hand, I do have. Sorry?
I convince you to call that element 1 instead of 0?
Yes, no problem. We can also. Yeah, the unique 0 is also a strict element, but 1 is the unique invertible strict element. Yes. Okay, so here is the proof plan. It goes as follows. So the first thing is to prove that P acts invertibly on the strict Picard spectrum of the P-complete sphere. And that's the most crucial part. This is where the core of the argument lies. All the rest is pretty formal. The second part is to compute the contributions to the strict Picard spectrum of the P-complete sphere away from P. And then the third part would be to assemble the information from the P-complete components to the computation of the P-complete sphere, to the computation of the strict Picard spectrum of the sphere. So there are 3 parts, and I will describe briefly all of them. So as I said, the first one is the most important one, and this is proving that P acts invertibly on the strict Picard spectrum of the P-complete sphere. So let's go into that. So the main player here is the Tate construction. So remember that if G is a finite group and X is a G representation in spectra, namely a functor from the classifying space of G to the infinity category of spectra, then we define the Tate construction to be the cofiber of the norm map going from the coinvariance to the invariance. So this is the map that takes an coinvariant class in X and symmetrizes over the group, summing of the group elements to get an invariant class. And the cofiber is called the Tate construction. So it is some kind of invariance, modulo invariants, which are invariant for Boring reasons, in some sense. And these have various interesting features, this construction. So first of all, it is Lax symmetric monoidal. So there is a canonical map from the tensor of 2 Tates to the Tate of the tensor. And also, if I denote again by pi the terminal map going from BG to the point, and X is any spectrum, then there is a canonical map going from X to the Tate construction of the trivial G representation on X. So it goes by going from the unit from X to the fixed points of the trivial action. So this is just the unit of an adjunction, and then following it by the canonical map going from the homotopy fixed points to the Tate construction. This map is usually called the canonical map. So it is canonical, but it's also its name. So it's called here can. So this is something we can do for every spectrum. And interesting feature of it, which is crucial for the whole argument, is that when restricted to the P-complete sphere, this canonical map is an isomorphism. So the Tate construction on the P-complete sphere is just the P-complete sphere. And this is a theorem of Lin and Gunawardena, and it is known also as the Siegel conjecture, although it is a theorem. And we are definitely going to use it when computing the strict Picard spectrum of the P-complete sphere. Another interesting feature of the Tate construction is the so-called Tate diagonal, which is something very special to spectra. So let me then change a little bit, abuse a little bit notation, and let's theta P of X for X spectrum, the total P power, but remembering only the cyclic action and not the whole sigma P action on it. So only cyclic permutations of the terms. Then there is the following theorem of Nicholas Scholze, and a version of which, defined by Lunen, Nielsen, and Rognes, is that there exists a unique Lax symmetric monoidal natural transformation, delta P, or rather, for every spectrum X, there is a natural map which laxly preserves the tensor structure, going from X to the Tate construction of its total P power, tensor power. So the idea is that this should come from the fact that spaces have a diagonal map going from X to the P, which is invariant under the cyclic permutations, and this is like a spectral analog, the Tate construction being the thing you have to replace by the fixed points we had before. And very importantly, if X is P complete and bounded below, so have only homotopy groups from some point and above, then this map is an isomorphism. So this again should come from the fact, is related to the fact that the fixed points, but now in the set theoretic sense, fixed points of the cyclic action on x to the p are just the image of the diagonal map from x to the p. But this is some kind of a spectral version, which is very interesting.
Excuse me, Shachar,
yes.
Excuse me. But if you use, instead of the cyclic group, the full symmetric group, it seems like all of the statements, all the interpretation of the statements would also hold that the fixed points of this for spaces, the fixed points of the symmetric group action would also be diagonal.
Yes, okay, so this was all analogies just to get intuition, but to make
yeah.
this result actually work, we are highly using the fact that the group is a P group and the spectra are P complete. So there is a theory here which is non-trivial, and I mean, this was all in order to get some kind of naive intuition, but the actual proof involves the P completeness and the group being a P group. So it's kind of a non-trivial thing.
Okay.
Yes. In fact, this result, which is it can be used actually to prove the previous one, that the canonical map is an isomorphism, because once we have an algebra which is somehow isomorphic to the unit, then every algebra map from the unit, from the P-complete sphere to it is an isomorphism. So the fact that the diagonal is an isomorphism for the P-complete sphere implies also that the canonical map is. So actually, this is a proof of the previous result, one of the proofs. Yeah, so let me now tell you what are all the players which are going to play in the proof that P acts invertibly on the strict Picard spectrum of the P-complete sphere. So we have the total P power map, which for now we think of as a map from spectra to spectral CP representations, or functors from BCP to spectra. We have the trivial action functor, which takes a spectrum to the trivial CP action on it. And on the other direction, we have the Tate construction, which takes a spectrum with a CP action and turn it back into a spectrum. And those are related by the following two natural transformations. We have the canonical map that goes from the identity of spectra to the Tate construction on the trivial action, and the Tate diagonal that goes from the identity to the Tate construction on the total P power map. So as you see, the source is the same, and the target is similar, but not quite the same. Okay, and now we are ready to prove our results. So first of all, first computation is at pi 0 of the Picard spectrum of the P-complete sphere, which is just the set of isomorphism classes of invertible P-complete sphere modules. It is just Z generated by suspension. So every invertible module over the P-complete sphere is a suspension of the P-complete sphere. So this is a very small piece of the Picard spectrum. Of course, it have infinitely many other homotopic groups which are related in complicated ways, but that's a start. So now we take X in the Picard spectrum of the P-complete sphere, so an invertible module over the P-complete sphere. And we see the following things. First of all, because it is secretly a suspension of the P-complete sphere up to a non-canonical isomorphism, but still, it is bounded below, because this is a property that is, you can just check, no matter how you identify something with a suspension of the P-complete sphere, it is bounded below. So by the result of Nicolaus and Scholze, the Tate diagonal map is an isomorphism. Another thing is that if we evaluate the canonical map at the Pth tensor power of X, it is also an isomorphism. And here this is because it's a suspension of the sphere. So for the P-complete sphere, it was the canonical map is an isomorphism. And of course, this property is stable under suspensions. So it's true also for any suspension of the P-complete sphere. So the canonical map is an isomorphism. And deliberately, I decided to evaluate it at the Pth tensor power, because this is what I'm going to use next. So now if X is a strict Picard spectrum, then if you remember, I spent some time explaining how the total multiplication by P maps act on the strict elements inside a spectrum, and they come with a canonical trivialization of the total multiplication by P map. So that means that for strict Picard spectra, we have a natural isomorphism between the total Pth tensor power and just the trivial action on the total P tensor power. So just tensoring X with itself P times, and then let the cyclic group act trivially is the same as tensoring X with itself P time and let the cyclic group act by permutations. And that's exactly because we looked at something which is in the image of a map from the integers, so that on the source it's true, so it's also true on the target. So now we just combine everything and we're going to get a cool equation. So X, which was now an element of the strict Picard spectrum of the P-complete sphere, is the same as, by the Tate diagonal, as the Pth equivariant power of X, and then apply Tate construction. But now, using the implication we had before for strict Picard elements, this is the same as the Tate construction for the trivial action on the Pth tensor power. And because of the inverse of the canonical map, that's just the Pth tensor power of X. So we started from X and we ended with X to the P, which is very weird equation for an element. So in particular, that means that the strict Picard spectrum is actually P minus 1 torsion. And in particular, P acts invertibly, because every P minus 1 torsion spectrum have an invertible multiplication by P. So this is the main part of the whole argument, that the combination of the canonical map, the Tate diagonal, and the strictness of strict Picard elements give rise to the equation 1 equals P. Okay. So now we are going to exploit it to just compute the strict Picard spectrum of the P-complete sphere. So the first thing is that now, once we know that P acts invertibly, we can actually compute the thing with P inverted at the beginning. So the claim is that now the strict Picard spectrum of the P-complete sphere can be equally defined as maps, the connective spectrum of maps out of Z with P inverted. And well, the reason is very simple. Because P is invertible, we can as well replace the object by the inverse limit of multiplication by P. But that's an inverse limit of maps out of Z, which is a map out of a co-limit. And this co-limit is by definition Z of 1 over P. But now the advantage is that we are mapping from a spectrum on which P is invertible. So that means that everything which is at P on the target can be eliminated. So in other words, now we are left with computing the strict Picard spectrum of the P-complete sphere away from P, by which I mean computing maps out of Z with P inverted. That's what I mean by computing away from P. So the observation here is that if I take the simply connected cover of the Picard spectrum, namely ignoring pi 0 and pi 1, all higher homotopy groups are like the homotopy, or some shifts of the homotopy groups of the P-complete sphere, which are derived P-complete abelian groups. So that means that this spectrum is P-complete. In other words, this spectrum is the inverse limit of its quotients by P to the n. And therefore, because on Z adjoint 1 over P, P is invertible, and on the target is P-complete, so it's an inverse limit of P torsion things, there are no maps from one to the other. And that means that like almost all of the Picard spectrum does not participate in computing the strict Picard spectrum, only a very small piece of it. So in other words, we have now the following sophisticated way to write the Postnikov tower of the Picard spectrum of the P-complete sphere. So we have the simply connected cover, we have the Picard, and it turns out that the one truncation of the Picard is actually just the Picard of the pi 0, which is ZP, because pi 0 is still Z and pi 1 is just ZP cross. So it's a short way to write the tau smaller than or equal to 1 of the Picard spectrum of the P-complete sphere. So now we can map into this fiber sequence Z of 1 over P. And because on the source there are no maps, we just get an identification between mapping to the middle thing and mapping to the right-hand side. And right-hand side have only 2 homotopy groups, so this is now a finite computation. So we are left with the classical task of computing maps from Z1 over P to the Picard of ZP. And well, the Picard of ZP is built out of the suspension of ZP cross and Z. This is a special case of what I said about ordinary rings. And a funny thing, in connective spectra, unlike in spectra, there are no maps from Z1 over P to Z, because I cannot divide an integer by P infinitely many times. So as long as I only care about the connective part, this doesn't participate as well. And we get that the strict Picard spectrum is just maps to the suspension of ZP cross from Z1 over P. And this can be just computed. It's a map between Ellenberg-MacLane spectra. So we just have to Z linearize the source. The target is one truncated, so we can as well one truncate the source. And then, well, classical computation, of the integral or maybe p-localized integral homology of Eilenberg-MacLane space tell us that that thing is just Z1 over P. So this is about the nth Eilenberg-MacLane space of Z not having age n plus 1. So it's just now maps in the derived category of abelian groups from Z1 over P to the suspension of CP cross, which turn out to be the suspension of FP cross, because this is the part which is can be infinitely divided by P. All other things cannot, because there is a CP component. So this finishes the computation of the strict Picard spectrum of the P-complete sphere. And finally, I wanted to assemble the Picard spectrum of the sphere from the Picard spectra of the various P-complete spheres. So let me just recap a little bit. So we have shown that P is invertible on the P-complete, on the strict Picard spectrum of the P-complete sphere. And using this fact and the fact that the Picard spectrum is mostly P-complete, we were able to reduce to a computation related to the Picard of CP, which is the pi 0. And then we just computed it and got the suspension of FP cross. And this suspension of FP cross is now really just the Teichmuller lifts of elements of FP cross lying in pi 1 of the Picard spectrum. And now the question is how to relate those various strict Picard spectra of the P-complete spheres to the strict Picard spectrum of the sphere. And well, this kind of gluing procedure is usually called the arithmetic fracture square. So let me denote by A, the rationalization of the product of all the CPs, and this is also known as the ring of finite adels. So it is a tuple of elements of the various QPs, but in such such a tuple which have only finitely many denominators uniformly. So almost all elements are actually periodic integers. And then the sphere spectrum participates in the following Pullback square of infinity rings. So we have the sphere, it maps to its rationalization, which is just the discrete spectrum on Q, and this have to do with the fact that the higher homotopic groups of sphere are all Gaussian. It also maps to the product of all its P completions over all primes P. And those things meet together in the finite adels to glue the sphere. So there is such a Pullback square. So in other words, an element of the sphere can be thought of as a rational number, a tuple of elements of the various P-complete spheres, which agree, and now it's really which agree at the adels, because adels are discrete, so there is a property of those things to be the same in the adels. Now, the problem is that Picard is not a pullback preserving functor on rings, so this doesn't immediately give us corresponding partition of the Picard spectrum of the sphere into pieces. But it turns out that this is okay. So a fact which is not completely formal is that now we can express the strict Picard spectrum of the sphere again as a pullback, where now what we have here is the suspension of Q star, which is now have to do actually with GL1 of Q, the suspension of A cross, which now have to do with GL1 of A, and then the product of all various strict Picard spectra of the P-complete sphere. Remember that this left down term we have computed, this is just a product of suspension of FP crosses. And again, this is not formal, but it's not very hard, because unlike Picard, GL1 and also GM are pullback preserving functors. The functors that take an infinity ring to its connective spectrum of units is limit preserving actually. And well, the Picard spectrum is only off by one homotopic group. So to make sure that there is such a pullback square, we only have to see that somehow pi 0 of the Picard doesn't prevent it from being a pullback square. And this is something we can just analyze by hands. So the key point here is that the strict Picard spectrum of the sphere is actually the same as maps from Z to the suspension of GL1 of the sphere. Or in other words, no suspension of the sphere is strict as a Picard. So like the only strict Picard element of the sphere is the sphere itself. It just might a priori be strict in many different ways. And this actually follows from the computation we had, because if we if some suspension of the sphere were could be refined to a strict Picard element, its P-completion could also be, but we have computed the strict Picard spectrum of the P-complete sphere, and since that this is connected, so only the P-complete sphere can be strictified as a Picard element of the P-complete sphere. So that proves this fact, and from this fact and the arithmetic fracture square, we can like play with it and prove it. So basically, the pi zero of all the various Picards doesn't play in the game in some sense, only their identity components. Okay, so well, we have a pullback square, and well, in this pullback square, the bottom left is what we want, and all the rest we know. So suspension of Q cross we know, suspension of A cross, well, we sort of know. At least we have only one homotopy group, and the product of all the strict Picard spectra of the P-complete spheres we know because we have computed it in point A. So now we can just write a long exact sequence of homotopy groups and see what we get. And this long exact sequence is actually fairly short. It is a 4-term exact sequence because, well, what we had here were mostly very truncated spectra, like all the terms except for a priori G peak of the sphere are one truncated, and a posteriori also that. So we get the following long exact sequence. So pi 1 of the strict Picard spectrum maps to the product of the pi 1s of the terms on the sides, which are product of FP crosses. This is from point A, and Q cross by definition of suspension of Q cross. This maps to pi 1 of the suspension of A cross, which is just A cross. And this maps to pi 0 of the strict Picard, and all the rest of the terms are 0. So there is no other terms in the exact sequence. So now all we have to do is to compute this snap in the middle, compute its kernel and co-kernel, and we got the computation of the strict Picard of the sphere. So here is how it goes. So pi 1 is the kernel, and it turns out that the kernel is 0. Well, that means that if we have an element of A cross, there is only one way by which we can present it as a rational number times a product of Teichmuller lifts. And why is that? Well, first of all, being in the kernel means that the rational number have to be plus minus 1, because if we had there some prime p, there is no element of the other component that can change the p valuation of the element. So it's really the same as just restricting only to plus minus 1 on the right term, and then of course the image is only the product of the CP crosses. But here something really funny happens. So the claim is that every element of the product of the CP crosses have a unique expansion as a tuple of Teichmuller lifts and a sign. And the reason is that, if we have such an element, if the right-hand component is 1, we are done, because then left-hand component is just a subgroup. But if it is -1, then it cannot be corrected at the prime 2. So this annoying fact that the strict units of Z are Z mod 2 because we have -1 is just corrected by the sphere, which I find nice. It's much more symmetric. There is no favorable prime that make trouble like in the sphere, unlike the integers. And pi 0, one can compute as well. And again, there is something funny happening at the prime 2, which actually make the answer relatively pleasant. And well, it is now the following sort of adelic quotient, A cross, now modulo Q cross, but unlike usual adelic quotients, now we are quotienting not by the product of the ZP crosses, but only the Teichmuller lifts. And it turns out that this action of this product of two groups have a fundamental domain, which is the following. So we take elements which are 1 mod 4 at the 2-AD component and elements which are 1 mod P at the every other prime. And the reason for this 1 mod 4 thing is exactly to eliminate this plus minus 1 here. So this is a fundamental domain, so it is just isomorphic to the quotient. And now it turns out that these subgroups are small enough that the periodic logarithm at every prime, including 2, just converges on them. And integral, so those are just, each of them is just a copy of the corresponding ZP, not cross, just ZP, and the product of the ZP is Z hat. So again, something quite delicate happened here to get rid of those annoying plus minus 1s we have in GM of Z and get much more uniform answers. So I consider it as a evidence that the sphere is better than the integers somehow. Right. So So this is it. I mean, I proved or at least outlined the proof of theorem A and theorem B. But I do want to talk about something. So this something is even more recent. It wasn't here on the previous version of these slides, but I recently realized that one can actually exploit this to compute more things. And I want to just present the results. So it turns out that the P-complete sphere is somehow a part of a family of interesting E-infinity rings, and those are known as spherical width vectors. So let me remind you what they are. So if kappa is a perfect FP algebra, then there is some kind of a sphere level or spectral level analog of the classical width vectors, which is I denote by SW for spherical width. So it is a P-complete connective E-infinity ring, which I denote by the funny thing C-alg of P-complete connective spectra. But that just means an infinity ring which is connective and P-complete. So no negative homotopy groups, and all homotopy groups are very P-complete somehow. Right, and well, those infinity rings have all sort of very nice properties. So first of all, they are flat over the sphere, and the pi 0 is the width vectors of kappa. Namely, pi n is just the same as the nth homotopy group of sphere base changed to the width vectors. In particular, pi 0 is just the width vectors, so for that reason, I think of them as some kind of a spectral analog of the classical construction of width vectors. Another thing is that their FP homology, which I denote here by just tensoring with FP, but that's like taking the FP homology of this spectrum, is just kappa again. Well, yeah, not for every spectrum we can, I mean, this is a very special property of an infinity ring. The tensoring with FP ends up with something discrete, but it turns out that for those specific infinity rings, it's true. And they are characterized by the following universal property that maps out of them is the same as mapped from kappa to just the pi 0 of the infinity ring modulo P. Let me not be specific about what R stands here. For a suitable collection of infinity rings, you can compute maps from the spherical width vectors by just taking the pi 0 and reducing mod P. So it's easy to map out of those spherical width vectors. The example which explains why I consider it as a generalization of the P-complete sphere is that the spherical width vectors of FP is just the P-complete sphere. So secretly what happened is that I could compute the strict Picard spectrum of the P-complete sphere because it was the spherical width vectors of a perfect FP algebra. That's what really happened. And maybe if I will have like a few minutes left before the end of next slide, I will also explain why it's good to be a spherical width vectors of something. But first, let me present the results. So if kappa is a perfect FP algebra, then the strict Picard spectrum of the spherical width vectors of kappa have a very simple formula in terms of kappa itself. Namely, its pi 0 is the classical Picard group, or what I denote by class group of kappa, which is just the pi 0 of the Picard spectrum of ordinary discrete kappa modules, so no suspensions here. And the pi 1 is just K cross. So like only Teichmüller lifts survive when you consider strict Picard elements or strict units in this case. And note that this direct sum is not surprising. I mean, computing a Z module or its homotopy groups is the same because, as I said, every Z module non-canonically, but still decomposes a product of its homotopy groups. So knowing this and knowing that pi 0 and pi 1 are what they are supposed to be and all the others are 0 is the same information. And corollary is that GM is interestingly rigid. So GM of the spherical width vectors of kappa and of kappa are the same. This is maybe a nice way to present the result. Actually, also the previous one can be said in a similar language, namely the strict Picard spectrum of the spherical width vectors is the strict version of the classical Picard, or rather it is just the classical Picard spectrum of kappa, which doesn't allow suspensions. So in this case, right, the bottom thing tells us that somehow GM is some kind of a rigid thing that doesn't see the fact that we turn it into a spherical infinity ring as long as it's sufficiently flat. And the first thing is telling us, in some sense, that strictifying the Picard spectrum have the effect of classifying it, namely killing all sort of suspensions and leaving only the things which are discrete. So that's how I would like to think about those two results. But in any case, this is a quite wide collection of infinity rings for which we can now compute those invariants. Yeah, so do I understand correctly that I am still having like 5 minutes or?
Actually, the talk is supposed to be 50 minutes.
Oh, I'm sorry. So I am already 5 minutes late. Sorry. So let me stop here. I'm sorry. That's my mistake.
Yeah, that's okay. That was so excited. I have to teach in like less than 10 minutes in a different building, but so I will have to quit pretty quickly. But first of all, let's thank Shachar for the very interesting talk. Are there any questions? Tyler.
Is there any chance of using these types of techniques to analyze like the strict multiplicative monoids rather than the strict like invertible elements?
Absolutely. So there are ways to think about this method which allow to compute also strict multiplicative monoids of higher things. In particular, yeah, we can similarly approach this. The method of proof allows also to analyze the strict multiplicative monoid of spherical width for every couple. Absolutely.
Go ahead.
Other questions? Go ahead.
I had a quick question about the computation. So that if G pick of the sphere is Z hat, there's a forgetful map from G pick to just pick, I guess, and pick their pi naught is Z.
Yes.
I suppose the map has to be trivial. If
it is trivial. As I said, the only strict Picard element is the sphere. It just has a Z-hat collection of strict structures. Yes, but definitely the map is trivial.
So they all land in the same component.
Absolutely. Yes, the map is the trivial map from the strict Picard to the Picard. It's the zero map of spectrum.
That's very weird.
Yes, I agree, but that's what higher algebra does.
Thank you.
Other questions?
I have a question about this result of Hopkins-Lurie that's unpublished. So I was a little perplexed that the p-adic integers popped up in n+1 instead of maybe the vit vectors with respect to that perfect field that you specified. Could you say something about that, or why is that the case?
Why do you see the Z, P, and not? Well, so do I have some quick response to that? I have to think about it. I actually don't see a reason why the spherical width should appear, but maybe I cannot answer like on the spot.
I think I'm also playing some free word associations, right? Because the Morava E theory for a perfect field with characteristic P, right? If you choose FP, you get the P complete.
Okay, maybe I can say something about it. So for every one way to think about it is that the Morava E theory, this component like the pi n+1 doesn't depend on the underlying perfect field, and well, this has to do with the fact that so you can think of it as some kind of a rigidity result. The strict Picard spectrum doesn't really change, or at least like GM doesn't really change when you move from one field to a larger one, and this has to do with the fact that the proof here secretly uses that everything lands in sort of Frobenius fixed points in the right sense. So like, the proof really uses the Tate valued Frobenius in some way. So that's maybe an explanation.
Scroll down.
Sure, thank you. And then I had one other question. So the
scroll down in the window you just closed.
The theorem in progress here, does this approach just follow the approach that you took for the P complete sphere spectrum? Like, is the essential input still somehow that P is invertible, or?
Well, they are organized slightly differently. So the main feature, let me just say what is used. What is used is that the spherical width vectors have the following two properties. its canonical map is an isomorphism. This is as before, and its state-valued Frobenius map is an isomorphism. So the general property is that the Frobenius image of a strict unit is the canonical image raised to the p power. That's the main ingredient. And it's very much related to what I said, but said maybe a little bit in a more generalizable way. But yeah, it's basically the same ingredients.
Okay. Yeah, there's a comment from Craig to everyone in chat. It's the Ravenel-Wilson computations.
That was about the Liam's first question about why you get Z and not Vit on K. Just yeah. Anyway.